Hello, Dr. Rhonda Cofield here. In this section, we're going to talk about the different types of equations in solubility, and that is molecular equations, ionic equations, and then net ionic equations. So a molecular equation is the equations that we have been talking about previously, where we have reactants. We have reactants that produce products, and the reactants react to form the products, and we told what state they were in, whether it was aqueous or whether it was solid, liquid, or gas. And so this is the molecular equation. It's just the molecules that are reacting, and they react, if you recall, in molar ratios or formula units. Metal cations are exchanging anions. That's how you predict what the product is going to be. What am I talking about? All right, so the anion in lead nitrate is NO3, and in sodium iodide is I-, okay? And so all we do to form the products is the sodium takes the nitrate, and then the lead takes the iodide, and they've just swapped, okay? It's just swapping anions. You do have to remember, though, how these are put together, which we learned about, I think, in Chapter 2, so that you will know that, the swap and drop with the charges, because remember, these are ionics, and so since, and you can get that from the reactants. So like, since there's two nitrates, and nitrate's always a -1, that's lead is a +2. So it's also going to be a +2 over here, okay? And so you'll have to have two iodides in the formula, whereas you only had one in with sodium iodide because sodium is only a +1. So you just got to watch that when you're making the products. So when we write those, we form the new products, and then we have to balance it, okay? And so make sure that you balance it, just like we learned. So we're taking all of these skills, and we're building until we get to this where we've made this reaction. All right? So once you've done that, then what you have to do is predict, are these going to be still aqueous, okay? That is, are they soluble in water, or are they going to be insoluble, forming a solid? And so that's the last part of that, especially as we're looking at reactions in ionic aqueous formats. So if we put them in, and we had the molecular formula earlier, when they go into solution, they're going to ionize, okay? So if you have Na2SO4, you're going to account for those ions. So you have one SO4-, but you have two sodiums. So when they form the ion, you're going to have two sodium ions. With barium hydroxide, you had BaOH2, so you're going to have a barium 2+ plus 2 hydroxides. You're just accounting for everything. Now, when you make the NaOH, it's still going to be soluble, and so you're still going to have sodium and hydroxide. But the barium sulfate, you got to go back and look at your solubility rules. You're going to see that a sulfate that is attached to a barium is insoluble, which means in that aqueous solution, you're going to form a solid. So when we show what the ions look like, that's called the Ionic equation. All right? And we show strong electrolytes they'll be going and they'll be turning into ions on the product side. The ones that are insoluble or predominantly molecules, like weak non-electrolytes, we show them this way. Now in Chem 2, or later chapters, you're going to see that it's relative how insoluble something is. But this just means it's very, very, very low solubility, typically. So soluble aqueous species are written as their ions, but the insoluble solids are represented by their chemical formula stating that they are in that solid state. So once we've written the ionic, we go through and we look. This arrow works exactly like an equal sign. So if I have something on both sides of an equal sign, they cancel mathematically. So the same is true for what we call spectator ions. So they're spectator ions because they're at a basketball game, they're watching what's going on, but they are not participating in the reaction. And so those spectator ions are those that occur on both sides of the arrow and cancel each other out. So what do I mean? Okay, so I've got sodium and sodium aqueous on both sides, so they cancel. I have hydroxide and hydroxide on both sides, so they cancel. So what that allows me to do then is write what we call the net ionic equation, which are the ions that react to form the solid in a precipitation reaction. So what I had left was the barium 2 plus, the sulfate 2 minus, forming barium sulfate, which is a solid. So the steps to determining molecular ionic and net ionic equations for these precipitation reactions, you write and balance the molecular equation. You got to predict those products and make sure you get the formula written correctly. Write the ionic equation by separating the strong electrolytes, those that are still going to be aqueous, into their ions, and then write the solids by their with the designation of S, leaving them in their formula, and then write the net ionic equation by identifying and canceling your spectator ions on both sides of the equation. Okay, so let's practice. So this says write the molecular, ionic, and net ionic equation for the reaction that occurs when aqueous solutions of lead acetate and calcium fluoride are combined. Okay, so it tells me they're aqueous solutions, which means those are water soluble. So I have lead acetate, C2H3O2, and that's aqueous, and it's important that you write that so we know that it is soluble, plus calcium fluoride, aqueous, and you can look it up on the chart, but you don't have to because we already know if it's an aqueous solution, it's soluble. All right, and so then the next thing we got to do is predict the products. So I'm going to take the lead, and instead of the acetate ion, I'm going to put it with the chloride ion. So it becomes lead. Now, chlorine, as you see here, is always a -1, okay? So it's a -1. In acetate is a -1. So the lead that was with the acetate is a +2 because it took 2 of those acetates to have a neutral compound. So I know that this is a -1, this is a +2, so it's got to be PbCl2. And then I'm going to swap the other one the calcium with the acetate. Calcium's a +2. We know from seeing this previous reaction that acetate is a -1, so there's going to have to be 2 of those in that as well. Now I've got to make sure that this is balanced, because if it's not balanced, I'm going to have to go back and balance it before I do anything else. Okay? All right, so in this case, it's balanced. All right, and you can always check that. 1 lead, 2 chlorines, 2 chlorines, 2 acetates, and 1 calcium. So it's balanced. So this is the molecular. The next step is to do the ionic. And all I'm going to do here is I'm going to take them and I'm going to break them out into their, oh wait, before I do that, I almost forgot. I've got to decide if either of these is aqueous or if they are a solid. And if you look on your chlorides, chlorides are typically insoluble, and especially when they're combined with a heavy metal like lead. And I just get that information from that table, okay, to say that lead chloride is a solid, and potassium acetate, all acetates are soluble, so they're aqueous. Sorry, almost forgot that step. Okay, so next I'm going to break those into their constituents. So I have lead 2 plus 2 C2H3O2 minus ions, and again they're aqueous, plus Ca2 plus 2 Cl minus. Remember, I have to do 2 Cl minuses instead of 1 Cl2 because Cl2 is a molecule. It is not an ion. So you have to make sure that you write them that way, that I say that there's 2 chlorides. All right? Then that's going to go to, if this is a solid, I'm just going to write that as the formula because it doesn't turn into ions. So PbCl2 solid, but the calcium acetate is soluble, so I'll say plus calcium plus 2 acetates, and again those are soluble, so I write those as aqueous. So that's the ionic. So all I did was, just like when we're putting things together, we look at the ions. When I break them apart, I'm doing the same thing. Okay? So once I've done that, I want to see what the net ionic is. So the net ionic, I'm going to cancel spectators. So I have 2 acetates on both sides, and I have calcium on both sides. And so what I have left is Pb2 plus 2 Cl minus, and they're again aqueous when they're doing this, and they are going to form PbCl2, which is the precipitate. If I form a solid, then I did have a precipitation reaction. If I do this and everything is still aqueous, then no reaction occurs. Okay, so don't be afraid to say that if all of this turns out to be soluble over here on your product side, then no reaction occurs. Okay? And that is precipitation reaction. Here are your the ones for you to practice. And one of those may not react because they don't form a solid. So everybody's a spectator. When we come back, we're going to look at more reactions in aqueous solutions, specifically acids and bases.